Do you remember when we talked about the very, very beginning of this course? And I use the analogy of learning about radians was like, hey, you're back, was like learning a new language. Remember talking about that? Remember what I told you? And I said, at first you're going to start by converting everything into degrees in your head, just like when you're learning a new language, you convert everything, like you translate everything in your head to your comfortable language, think in your comfortable language, translate it back. And you probably did that with radians in the beginning. And we may not have talked about this, but I promised you that if you did the work, by the end of the unit, you would be thinking in radians. How many people, you don't have to actually put your hand up, but how many people experience that? I'm curious, because that's often what happens. It's so strange at first, but by the end, especially by the end of the second unit, you're like thinking in radians. So logarithms are like that. This is what we're doing today. This is going to be a lot like that. It'll make a little bit more sense when we get into this, but we're going to do it like the day one day where we're translating. But by the end of this unit, if you do your practice, you won't have to translate anymore. You'll be thinking in logarithms. But I said this yesterday, it is crucial that you're doing the practice, because if you don't get to the point where you're thinking in logarithms, you will probably not find a lot of success in this unit. It's either really, really easy or really, really hard. Okay? So keep that in mind as we go through what we're doing today. And that same analogy, that you want to get to the point where you just understand logarithms and you're not fumbling with them. And in particular, just the notation. It's just a new notation is a big part of it. And you have to understand each part of the notation, what it means, how to write it, that kind of thing. And we will start today by translating into a language we already know, but we'll transition eventually to speaking the language of logarithms. So, how many operations do you know before we get into what we're actually doing today? How many operations do you know? Can you name them? Thank you. Addition, we'll start with addition. Can we do that? Okay. So I'll do an example of addition. Yep. 5 plus 3. Anybody know what 5 plus 3 is? Okay, I'll do this one. It's 8. So we have an operation. It's interesting because I'm glad that you picked up on this right away, but sometimes people don't understand what I'm asking when I say name the operations. And you're like, heart transplant? I don't know what you're talking about. But now we know what we mean by an operation, a mathematical operation. Remember the order of operation. We talk about BEDMAS, the operations, and these are all the ones. So we have adding. Now, what is the opposite of adding, which you already said? Subtraction. Why is it the opposite? Because if I take 5 and I add a particular value, in this case 3, I get 8. So if I take 8, the result of the adding, do the opposite operation but of the same value, so subtract 3, I get back 5, the thing that I started with. So these are opposite operations. Something that's interesting about addition, 5 plus 3 is 8, and 3 plus 5 is also 8. Is that true for all things adding? Good, yes. That's the property of being commutative. That's called commutative. If you studied mathematics in university, if you went into an area of mathematics called pure math, it sounds difficult. I guess it probably is difficult. But it's interesting because we do all this algebra, and then in pure math, you go back to just talking about the basics a little bit again, and things like properties of different operations and number systems and stuff. It's very, very high level, higher order thinking math. It's almost not doing math, but talking about math. Anyway, and you would talk about the different properties that different operations have in number systems and things like that. So it's commutative. I think it's the Wikipedia article of the word commutative that talks about real life examples of things that are commutative. So commutative to me is a word in mathematics, but I guess you could apply it to things in real life as well. Like the example is putting on your socks. If you put on your left sock, then put on your right sock, is the same as putting on your right sock, then putting on your left sock, right? Gets you to the same place.
Yeah, I don't like the other way. You gotta go left first.
Left first, then right?
Yeah. I don't trust somebody who goes right and left.
Well, hold on.
Different socks? Is there a left sock and a right sock?
Yeah.
Is this so? My entire life is a lie.
I've seen socks that have little slips for the toes. Those would have an order. But then it goes on, hold on, then it goes on to give a counter example, something that's not commutative in the same kind of example, and it's putting on your pants and putting on your underwear. The order for that matters. You can't do it in the wrong order. Some people maybe would, but typically you want to do that one in the right order. Okay, so anyway, so this one would be 8 minus 5 would give me back the 3. Okay, what's another operation that we could talk about? Somebody else? Division. Can I start with the first one, which is multiplication? Okay, good. So 5 times 3, 5 times 3 gives me 15, and the opposite of that would be division. So if I take the 15 and I do division of the same number, I get back the 5. And multiplication, just like addition, is commutative, where 5 times 3 is 15 and 3 times 5 is 15. But notice that 15 divided by 3 gives me back 5. Notice that neither of these operations are commutative. 8 minus 3 is not the same as 3 minus 8. And 15 divided by 3 is not the same as 3 divided by 15. I've written the same thing twice. I didn't mean to do that. Okay, doesn't matter. Anyway, we get that. So these are operations. These are interesting things. Now, you learn this in grade 1. You learn how to add, then you learn how to subtract. Awesome. Thank you. Right? Very soon after. Then a couple of grades later, you learn how to multiply, and then the next grade or so, you learn how to divide. So in mathematics, it seems to be this pattern where we learn how to do something, and then we learn how to undo it, because that's what these things do, right? If I add 3 to get 8, I subtract 3 to undo that. I do the opposite operation to undo something to get back to 5. And we know when we start solving equations, this is super useful, because when I have 5x equals 15, I should have put this one down here, this is multiplication. But if I want to undo that to figure out what x is, I do the opposite operation, I divide. Right? And if I do x plus 5 equals 8, I mean, you can solve this by inspection, I'm aware of that, but I would do the opposite operation to undo it to figure out what x is. And that idea of opposite operations becomes very important in algebra. And then we do something like, what's another operation? Thanks. Not going to help me right now. But you're right, it is, and we know how to undo that. Very good. Squaring something, so exponents. So 5 squared gives me 25. Square root is going to be the opposite. Square root of 25 gives me back the 5. This one's interesting, because so far we've got 5 squared equals something, and we know the operation that gives us that something. Right? This is a little equation, just like if I went back up to this one. I have 5 plus something is 8, or something plus 3 is 8, or 5 plus 3 is question mark. Like there's 3 spots here, and we can solve for all 3. Is this true? Okay. And it's similar to find this question mark versus that question mark is similar. Do we know how to find this one? Yes. We know how to evaluate an exponent, how to find the result. Do we know how to do this one? Yes, that's taking the square root to get the 5. What if we put the question mark in the last position? Where's that? How do we find that? Okay, good. So we do have a way of solving some of these from grade 11. So we're going to try one of these right now. So this is like the square root of 25 equals 5, by the way, if you want to write this down. I don't know that you have to copy this down. 5 squared equals 25. We just do 5 times 5. We know how to do that one. This one is the one that we still aren't sure. We actually do have we can do some trickery, is what I like to call it, to solve this one. But it only works in special cases. And it's still a good skill to have. But if we had an actual operation to solve this, wouldn't that be better? No. That works in this case, but it won't always work necessarily. Okay, so let's look at how you did solve these back in grade 11. What you would do is you would take 2 to the question mark equals, and you would rewrite 32 as a power of something. So 32 is which power of 2? Good, so 2 to the 5. And then we do these things called, if the bases are equal, we can equate the exponents. Equate the bases, equate the exponents. The bases are equal, the exponents must be equal. And we say therefore, and we always include the therefore, our question mark equals 5. Do you remember doing this? And people want to do it sort of the wrong way, and I'll maybe show an example of that later. Yeah, we'll show an example of that later. But if you were doing it by equating the bases and equating the exponents, this is how it would look. But there's not an operation here. We're solving by inspection. I have to figure out which power of 2 is 32. That's inspection, not an operation. And how is it going to work for us when we have to solve this question? What's wrong with trying to solve this question in the same way? Say again? Yeah, that's right. There's no nice power of 6 that gives us 100. So what's 6 squared? 36. What is 6 to the 3? Huh. So the one we want is somewhere between 2 and 3. Does anybody have a calculator? 6 to the 2.5, what's that? 88 point something, right? It's not exact. Okay, so now we're between 2.5 and 3, a lot closer to 2.5. Look how close that is to 2.5. That's close to 100. 216, not close to 100. So we're a lot closer to 2.5. So how about 2.6? 105? Oh, we're even closer. Okay, so I don't know off the top of my head, maybe how about 2.57? 99.9? Whoa, pretty close, eh? Good guess, lucky guess.
I got 2.575.
Even better, even closer, and we can keep going. It's not going to be a perfect number, not likely. So you could keep getting closer and closer and closer by extending how many digits you get accurate to. That's not the point of what we're doing today, so we're going to stop there. It's close enough for our, but that's not a very efficient method, right? But your calculator is doing something to calculate it, and computers are doing something to calculate it. There must be a way of calculating it other than trial and error. Oh, I don't know. Why don't we call this a logarithm? So this is what we're learning about. This is our new language. And what logarithms do is they find or calculate exponents. You could think about it like that, at least for now. And like I said, a big part of what you're getting today, we're going to kind of take 3 days to look at this notation and look at the properties. Today, we're kind of going to see a hint of one of the properties, but we're mostly just looking at the notation, which means rewriting it into a familiar form, translating it back and forth to get used to how it's written, and hopefully working towards thinking about it the right way. But then we're going to do 2 days on different properties and different kinds of questions that you can do with logarithms. So hopefully when you come back after the weekend, you will be feeling comfortable with this, starting to get it, starting to really feel comfortable. And then we move into solving some equations, and then it'll be kind of the end of it. We do a couple days on applications too. Okay, so we're called logarithms. I think whoever came up with this, or I guess maybe we ran out of nice ways of writing these things, because when they came up with the exponent, they came up with the idea of, oh, we'll just make it smaller and up a little bit high. And that's kind of nice. It's a nice way of writing it. It's nice and clean. But for this one, they weren't very creative. They're like, logarithms. Let's write log. So this is the notation that we use. We write out the word log. And the most important phrase that you need to say over and over and over again in your head as you're working through this stuff, I think at least, it's what I think of all the time when I work with this stuff, is the base stays the same. If you can remember to say that every time you're converting, I don't see how you could get it wrong. The base stays the same. What's the base of this? 6. So the base of the log is still 6. And then the other two things switch places, because that's the point. It's supposed to be undoing this, right? So the 36 goes here, and the 2 goes there. Remember, you're calculating an exponent. So the exponent has to be over there on the other side of the equals. But the most important thing to remember is the base stays the same, and the other two things just have to flip, and then you've got it correct.
Are we gonna find out what log does, or are we just gonna like?
This is what log does. We're asking the question, which power of 6 gives you 36? And log answers 2. What exponent on the 6, what exponent on the base would give you this value? It's 2. Remember when I said 2 to the 5 is 32? We had to figure that out by inspection. Logs calculate that.
Yeah, but like, it's like we don't know. We don't know. Like if this didn't work out to 2, we wouldn't.
Yeah.
Like
the log calculates that.
So, but what does the log do?
It's an operation.
Okay.
What does multiplying do?
I don't know.
You're talking about like the computer language, like how does a computer or a calculator actually do it? That's a question for another class. Okay, okay, so this is the notation. This is what it means. You need to become familiar with it. The base stays the same. The other parts switch. You also want to understand what we were just talking about. What log to base 6 of 36. What does that mean? It means what exponent would I put on the base to give me that argument, that thing. And in this case, it's nice and familiar. It's 2. We get it. Okay, let's try this one. What if I want to rewrite this in exponential form? What's the trick? So it's 3 is the base. And then the 4 is the exponent because it's on the other side. So it comes in and it switches places. And the other thing is you could kind of, when you have it like this, because you know how exponents work, you can probably just figure it out. Because you're like, well, 81 to the 4 doesn't give me 3, so that one's out. Right? 81 to the 3 doesn't give me 4, that one's out. You might be able to figure it out, but we need to understand how this all plays together. Any questions so far? All right, let's try some of these. Yes?
Can you reduce this to like it's more like simpler, what is it called? Not function. Like,
Operation?
Operation, yeah.
Like what?
So like you can like reduce multiplying to like addition, and you can reduce exponents to.
Yeah, I don't think so.
Okay.
It is a bit of a different one. Well, some calculators have a log function, and it's really easy to use. If it doesn't, then you maybe don't. We'll talk a little bit more about how to use. Does your calculator have a log button on it? If anybody's calculator doesn't have a log button on it, you'll have to find one. Some of them have more fancy log buttons. Some of them have simple ones, but that's in an upcoming lesson, so you don't have to worry about it for now. Now here's where we're going to do two things, like I talked about at the beginning of this lesson. This is the old way of doing things, and this is how you're going to do it to begin with. But you don't want to always be doing it this way. We start out by converting it or translating it into a language we are familiar with, which is exponents. But eventually we get to the point where we don't have to do that anymore. That's what you have to do. So how would I rewrite this in exponential form?
2 is going to be the base, and x is going to be the equals to 8.
Equals 8. Good. And then we do the grade 11 way where we rewrite this. Whoops. There's your answer. 2 to the 3. And we always say therefore, because at least up until now, there wasn't an operation that was going from one step to another. It was just by noticing the fact that if the bases are equal, the exponents must be equal. It was like a conclusion that we were drawing. It was a deduction that we were making. Therefore, x equals 3. Most of these are here's what you don't want to write. This is a grade 11 mistake, because in grade 12, we're not even really doing this. We're only doing this to start. You better not make this mistake, but people go like this. 2 to the x equals 8. 2 to the 3 equals 8. So x equals 3. And the problem is lots of people are fine with this, but math teachers are not. What do you think is wrong with this? Why would a math teacher not like this? That's exactly what I would say. Where did the x go? You wrote one line, the next line has no x, the next line does have an x. So this line flows better. This one's also not going to be as good for solving harder ones that have like more stuff going on. This won't work, and this way will. So this is definitely not how you do it. But we're going to get to the point where we're not even using exponents anymore. So we will move past that. All right. Let's do this one. Go ahead and do this one. So this right now, mostly the practice is just rewriting in exponential form. That's what we're practicing. Everybody get 2? Okay. Stop me if there's any questions. This one's a bit trickier. The other thing that we're doing sort of today, we did this a little bit yesterday, but remembering the different properties and rules around different kinds of exponents and powers and that sort of thing. Remember, I often think of log as a question. It's a question that's asking, what exponent would I put on 4 to turn it into 1/4, 1 over 4? That's what it's asking. So I'm going to rewrite it like this. 4 to the x equals 1 over 4. Roberto, what do you think?
X equals
-1. So I'm going to show that extra step in there. 4 to the -1. Very good. Flips the fraction into a 1/4. So x is -1. We okay with that? Okay, 2 easy ones. I'm going to do this one quickly. 10 to the x. Powers of 10 are important, right? So we just kind of review them quickly. It's got 2 zeros. So it's the second power of 10. What exponent would I put on 10 to get 100? 2. What I'm saying is eventually we want to get to a point where there's no x, and we're going to see that momentarily, but where there's no x, and we don't rewrite it like this. We just say, oh, that's equal to 2. Just like when you started with exponents and you were doing 5 squared, and you'd be like, okay, it's 5 times 5 equals, you'd write it out the long way into something more familiar, which is multiplication. That's what we're doing here. That's not what we're doing all unit. We eventually get to the point where the question looks like that, and you write equals 2, because you just evaluate it, just like everything else. 5 times 3, 5 plus 5 plus 5. Do you remember doing that back in grade 1 or grade 2? All right, another easy one. 10 to the x equals negative 100. Who wants to answer this one? Is it a half? That's not an answer, that's a question. Does anybody think it's 1/2? You cannot square or take any exponent of something and get a negative. If the base is already negative, you can. That's tricky though with logs, so we don't do that. But so if it's like negative 2 cubed, you can get, but you're exactly right. It's an error. Did you do it on your calculator? Yeah. Cheater. I heard a couple other people say that it doesn't work. It's not possible. That's exactly right. This is not possible. We will revisit this at the end of this lesson. Not possible. The argument, remember when we talked about this before? This is the argument of the log. This is the base of the log. This is the result of the log. This is the argument of the log. The argument of the log cannot be negative. Okay, and that's going to be an important thing throughout this whole unit. We get into solving equations and different things like that. Okay, so this is not possible. People think it's negative 2, but we know negative exponents turn things into fractions. They do not make things negative. People might think it's a half, but what is an exponent of a half? That's a square root. So that'd be the square root of 10, which makes it smaller. So that's not going to work either. Question? If the 10 was negative. But logs don't work with negatives. But by inspection, what Isaac's saying is negative 10 to the 3 is negative 1,000. That's true. But logs don't do that. We'll talk more about this later, but try putting that into your calculator and see what happens. Yeah, did you try it? It still gives an error. Logs don't work. It'll be a bit clearer why exactly that's an error later. All right. How about this one? Let's rewrite it first. You're going to need brackets around the 1/3 to show that the exponent's on the whole thing.
The answer x equals -2, so 1/3 to the exponent of -2.
1/3, whoops, 3 to the exponent -2. So if we break this down, the negative will flip it back to a 3, and the 2 will square it to a 9. So the right side of this will become 9. Therefore, x equals -2. Good? Again, just getting familiar with using this notation and remembering some of this stuff about exponents. Yeah, you should be writing therefore there. It's a small thing. Just try to get in the habit. Okay. How is this one different from the other ones we've done so far? Seema? It doesn't have an equal to. So don't write this down. This is what people will do on a test when this question's on there. They'll say 2 to the x equals 64. 2 to the x equals 2 to the... And I'll be like, what in the world is this person talking about? Where did x come from? There's no x in this question. Where did the x come from? But because that's how we were solving it before, people want to solve it this way all the time. Okay? And if you are determined to do that because you're not ready to do it with just logarithms, then this is what you would do. You would say, let x equal log base 2 of 64. Then 2 to the x equals 64. 2 to the x equals 2 to the, thank you, 6. Therefore, x equals 6. You would require that. Okay? Because there's no x in this question. But this is what I was talking about before. What you want to get to is you want to get to the point where you don't need the x and to rewrite it as an exponent anymore. So I'm going to show you a little trick, and then eventually you're even going to be able to skip this trick. How did we solve this? By rewriting 64 as a power of 2. So I'm going to do the same thing. Equals log base 2 of 2 to the 6. And then what's the answer? 6. Right? And again, this is, if you don't quite get this, for now it's okay. We're going to talk about this again tomorrow more formally. But think about what this is saying. What power would you put on 2 so that it's equal to 2 to the 6? Well, I think you'd put a 6 on it, right? Because it's like 2 to the 6 equals 2 to the 6. So whenever you have the same base in this, it's going to be the exponent. What power would you put on the base so that it's equal to that thing? So it's got to be 6, right? So we can avoid the use of the x by just rewriting the argument in terms of the base here, and then just the answer will be that exponent. That's actually an important log property, but we're going to talk about that more tomorrow. For today, it's just a little trick that we can use to solve these without x. If you want to use x for today, it's fine. Please do it like this. I mean, in your homework, I don't care what you do, but on a test, you would have to do that. You would be required to write a let statement. But by the end of this unit, you should not be required to do this anymore. You should be able to do this. In fact, we'll skip that step entirely, and we'll just be like, oh, it's 6. I know what exponent you need. It's 6. I don't need to rewrite anything. We just evaluate. So what exponent do I put on 4 to turn it into a 64? 3. So this equals 3. What exponent do I put on 1/8 to turn it into 64? This is where you kind of have to break it up into 2 parts. Did you do it on your calculator?
I checked my answer.
Okay, good. Go ahead.
-2.
Good, -2. So 8 squared is 64, but because it's in the denominator, I got to flip it to the top. So -2. No, you don't need to write the box. I'm doing that like for the note, just for like So people say like we're trying to fill in this empty box kind of thing. Ooh, this is a tricky one. Unfortunately, this is the one that catches people and they don't know what it's asking and they leave it blank on a quiz or a test. And almost certainly this question will pop up on a quiz or a test. So this is log base 10 of 10 to the 0. So this equals 0. Right? Memorize that one if you have to, if you struggle thinking through those ones. But that's supposed to be an easy one. Log base anything of 1 will be 0, just like anything to the exponent 0 gives you 1. Same thing but backwards. Good question. We haven't totally decided yet because it's still a little ways off, but usually we do a no calculator quiz or no calculator part of the test. And then the rest of it, you get to use your calculator because there's some parts that we're going to need a calculator for. But when we make no calculators, the numbers are all small. So you need to know some of the powers. But importantly, you need to know the properties, so you can't just use your calculator and get answers. Go ahead and try this one. I think most people would check their answer for this on a calculator, but they would think, well, it's not 2. Try 3. Nope. Try 4. And it works. Right? So you might just try a few until you get one that works. And if you do enough of this practice, you'll see all of them and you'll eventually get to all of them. Last one. See if you can do this one. How many people have an idea? 1, 2, I saw 3 before. No? That's it? Okay. Yeah? How do you make something smaller? One-third. Is that what you were thinking? Good. Because, so this is equal to 1/3. Because the cube root of 1,000 equals 10, or 10 to the 3rd equals 1,000. Right? Okay. So that's notation. We're going to do one more thing today. Oh, come on. There we go. Who remembers the inverse from grade 11? You would have done a couple of days on this. You remember hearing of it, right? At least. Does anybody remember what you actually do to find the inverse of something? There's one thing you have to remember. It's like if you can remember this one thing, you can usually work everything else out, or almost everything. What do you think? Not quite. That would be true if it was x squared. The inverse of x squared is the square root.
Is it the square root? It's like the square root symbol, but with x as thing outside of it equals 2, or like.
Okay. That's not going to work, but you're right. Yeah, you could write it that way. Somebody else have their hand up? Nope.
Is x equals 2 to the left?
Okay, so, but what we do, if you remember, we switch the x's and y's, or we interchange the x's and y's. So yes, it becomes x equals 2 to the y. But we need to rewrite this in terms of y. And the logarithm is the thing that pulls the exponent down. This is why it's so useful. It calculates exponents. If I want to know what the exponent is, the logarithm gives me the value of the exponent. And remember what I said, that important phrase is, the base doesn't change. And the other two things switch places. So the inverse of the exponential function that we conveniently talked about yesterday is a log function. Graph y equals 2 to the x and its inverse. You could just sketch it. You don't need grid paper, I don't think. Try to do a moderately accurate sketch. So our asymptote, I'm going to do the exponential function first. Our asymptote is at 0. And remember, just picking some values. 2 to the 0 is 1. The scale is funky on this graph. It's confusing. 10 squares is 5. So 2 squares is 1. Don't get fooled by that. Same going the x direction. So if I go over 1, 2 to the 1 is 2. And 2 to the 2 is 4. 2 to the negative 1? A half? 2 to the negative 2, a quarter. We don't need to do all of these. An eighth, a 16th, a 32nd. See, we're exploring right now. We used our rewriting abilities to figure out that the inverse of the exponential is the logarithm function. Now we're exploring by graphing the inverse to see what the graph of the logarithm looks like. And the graph of the logarithm is going to tell us some really interesting things. So remember what I said about inverse? Interchange x's and y's. So if this point is 0, 1, what's my logarithm point? 1, 0. If this point is 1, 2, what's my logarithm point? 2, 1. If this point is 2, 4, my logarithm point is 4, 2. This is negative 1 and a half. So I go a half, negative 1. Negative 2 and a quarter. So a quarter and negative 2, and so on and so forth. Where's the asymptote of the logarithm function? It's on the y-axis, y equals 0. Good. Remember when we said log base 10 of negative 100? So that would be like, let me write this down. This one is y equals 2 to the x. This one is y equals log base 2 of x. Can I put negative x values into this function? I cannot. I cannot put negative x values into this function because it would be here, and this function does not exist on this side of the graph. So it doesn't make sense to put them in. Remember yesterday when we talked about the graph of y equals -2 to the x? Remember doing that yesterday? And it's like it flips back and forth between negative and positive, and we said this is not something we can graph. So how would you do y equals log base -2 of x? Like it wouldn't make sense. So even if you can do -2 cubed is -8, it's not gonna work out nicely. So the log function does not work with negatives there or there, but a negative y is fine. We just did that a bunch of times in our lesson. We'll talk about that more. Okay, we're gonna do one. Everybody okay with this? This is just graphing the inverse of something you did in grade 11. And this graph in particular, where the asymptote is going to be really important for like later on some of the stuff that we talk about and do. One more, let's graph one more function and its inverse. This one's 1/3 to the x, which has an asymptote at 0 again. So everybody look up here for a minute. 2 to the x did this. It started small and it did this. What do we call that? Increasing. That was 2 to the x. 1/3 to the x, therefore, is going to be decreasing. So we know that it's going to go like this. So 1/3 to the 0 is 1. 1/3 to the 1 is 1/3, right? So it's getting smaller. I'm going to go back the other direction. What's 1/3 to the -1? Thank you, 3. 1, 2, 3. And 1/3 to the -2 will be 9. So it's going to go off the graph already. But it's like doing powers of 3, but the other direction. So the asymptote for logarithms is the y-axis. Of course, you can do transformations on logarithms as well. Okay, and again, just interchanging the points, just taking the inverse of the points. This is 0, 1, so I go 1, 0. This was -1, 3, so I go 1, 2, 3, -1. This was 1, 1/3, so I go 1/3, 1. And the graph looks like this.